Welcome also from my side. I'm Kevin Mika. I'm a research associate at the Bielefeld University. I will give a quite deep dive into the VEDLIoT hardware platforms, going over these fancy boxes that we saw and telling you a little bit of the accelerators we have looked at and present you some of the benchmarkings we did. So, starting with the big picture again, we are now going over the hardware platforms that we are supporting inside the VEDLIoT project. So, as you can see on this page, we have 4 fancy boxes that we are supporting. This is the Rex system, the resource efficient computing system, and we have cloud appliances that support many microservers. We have Edge appliance that supports only 3 microservers, and inside the projects we are developing the Edge IoT device that is supporting 2 small microservers. So as you can see, we are trying to cover the whole thing from the far edge to the cloud appliance that you can work inside the same system. And maybe you can go about that in a research project with just sticking a few eval boards together and then using them. But that is quite hard when you get to more microservers that are stick together. And so we are providing a platform that offers manageability and a very, very good communication infrastructure. And we are starting now with the cloud computing appliance. We have two different carriers where microservers are plugged in. Microservers are these things here. These are complete computers. So they have the CPU, the memory, and everything you want on a pluggable board. And we can plug 3 of these big microservers into one of these carriers, or we can plug 16 of smaller microservers into this carrier. And as you can see, maybe you noticed this one. This is the NVIDIA Jetson TX2 module. It's a little bit older, but the NVIDIA Jetson family can be familiar to you. And we are allowing 60 microservers in one carrier and can have up to 15 carriers in one box. So we can have up to 144 microservers in one system in one box. Additionally, you can plug in a normal PCIe-based accelerator. And the cool thing now is that we have infrastructure that supports networking, management, and the I/O to the outside. So even if you have 144 microservers plugged in the Rex system, in the Rex box, you can access each one of them via KVM and also access them via the network. So going over the architecture, we have one microserver module. It's always the same. It has some CPU, some memory, and some I/O. And then we have the baseboard. We plug in more microservers on the baseboard and have more baseboards in the server. Then we have a distributed monitoring and KVN system that you can have the computer video mouse support, that you can go to the microserver and debug if something is wrong. We also have the serial output of the microserver. We also have iKVM support, so you can go there over the network. You don't have to go downstairs into the server room. You can do it from your office. Also, we provide power measurement. I will go into that in a little bit more detail in a few slides. Then we have normal Ethernet communication for management and normal computing. So we have 1G and 10G Ethernet on the microservers, and we have 40 gigabit Ethernet uplinks on the backplane to the outside. And then we have this high-speed, low-latency communication. So we are implementing PCIe switches to connect the PCIes of the microserver modules together. And with that, we can communicate over PCIe. So if you use a lot of microservers and want to implement these distributed compute systems, compute networks, then you have to have a good communication so that you don't hang up in latency or bandwidth problems. So we have this high-speed, low-latency communication on the Rex box. Additionally, we can provide storage to each of the microservers. Again, via PCI Express, you can plug in an NVMe storage device and share it to every of these modules via the SRIOV function. So each of these modules can access the same NVMe storage device. So you have a fast storage, fast shared storage on each of the microservers in your system. I promise I won't go into that detail anymore, but now we have that covered. We can go on and look at the T-Rex. It's the little bit smaller platform. As you can see, it shares a lot of the things with the Rex box. As it is an Edge appliance, we have put in a lot more interfaces. So we are providing video and camera output if you need that. So for the smart mirror use cases, we are using the T-Rex at the moment, and there we need these camera and video input outputs. So that is why the T-Rex is more focused on that. We also supply a different form factor of module here, but we will see that when we come to the microservers. The PCIe infrastructure here is again with a PCIe switch, and we also have direct connections between these different modules. So what we can do, we can not only like have a stern topology where we connect the modules together with a PCIe switch. So if we have a normal classical CPU-based system, we have these CPUs all connected via the PCIe switch, and then the modules can communicate and share their data. Or another thing would be a CPU-centric approach where you have the CPU which is managing two accelerators and doing some input-output stuff or management functionality. But we also can have a little bit more fancy topologies like a ring where you have the ring but communicating via PCIe, or a ring where you only have FPGAs. You can use native protocols because it's not bound to be PCIe, the connections between the modules in the left-right, we can use any protocol you want. So if you have, for example, a processor that has some chip-to-chip communication, you can also use that here on the T-Rex. Coming to the Microrex, the lowest appliance for us, the smallest. Again, as for the other housekeeping stuff like Ethernet communication management, connection via PCIe, but a lot more I/O. So now that we are on the edge, we want to connect as many sensors as we can to the module. So we have a whole bunch of input, outputs, everything you can want really. And we are focusing a lot more on wireless communications. So we need to support wireless LAN, LoRaWAN, 5G, the whole stuff. The setup for the Microrex is a little bit different as for the other ones. So we have two modules. One is the SMART 2.1 standard. You can get a lot of different modules for that standard already. And the other one is the NVIDIA Jetson NX form factor. Many of you will know this form factor. And we have two accelerator slots, one with M.2 and one with MPCIe. And there you can also plug in different accelerators. And then you can connect them. On the other systems, we are using a PCIe switch. So in runtime, you can reconfigure your system. So if the needs change, you can change the system. You can change the connections between the modules. This is not possible on the Microrex because here you set up once the system, and then you need to decide how do I want to connect these modules, plug in the correct COM brick, and then you're going. Additionally, we have gigabit Ethernet, USB for accelerators or whatever, a board managed controller that has directly integrated Wi-Fi, Bluetooth Low Energy, and LoRaWAN, which provides all the housekeeping stuff, turning on modules, turning them off, and doing the power measurements. Also, one thing that is needed for the Microrex, it has to be battery operated. So for the automotive use case, we don't have any wall plug power. We need to be battery operated. And this is done via a USB Type-C power plug. You can use a normal USB Type-C power bank, as you have for your notebook maybe, or a normal 12-volt battery. As we said in the beginning, we have done a lot of benchmarks. And for these benchmarks, we need some kind of power measurement. You can use the internal power management of the modules. They mostly provide some kind of information, how much power they are using, but this is mostly not accurate because it's mostly not seeing what the memory is drawing and what the miscellaneous stuff on the module is drawing. So we integrated power measurement for all the modules, and you can access that via Grafana interface or the Web GUI. And there are all the sensor data available with a 1 Hz sampling rate. But when you go into more detail and want to benchmark a certain algorithm, then you maybe want to have a little bit more resolution. So you want to see which part of the algorithm is drawing how much power. And for that, we integrated an oscilloscope mode. This can be activated for one module at a time. And as you can see, this is the web interface for it. It resembles a normal oscilloscope quite well. You have your X and your Y axis, and you can set triggers, can select channels. It's like if you know how to use an oscilloscope, you can use our integrated oscilloscope mode for the Rexbox system. Yeah, and it's really quite like having a current clamp on a normal oscilloscope, but you don't have to have all this hassle with how can I adapt it, how do I get to the power. So it's very easy to get these measurements for the different microservers. Talking about microservers, I'm going now over a selection of microservers that we support for the different systems. So for the Rexbox, we support the COM-Express form factor, and you can get a whole lot of different modules from them. Normal CPUs, ARM CPUs, you can get FPGAs like a Xilinx Zynq or Intel Stratix 10. And then we also support the smaller modules, the Appliance standard and the NVIDIA Jetson standard. So we have a quite old Exynos module, and we also have a small Zynq processor. So you could have up to 144 of these small ARM processors in one system and use them to do a dedicated task. These are modules that are developed inside our department, not directly inside VEDLIoT, but they have been developed by us. And this is the overview for the T-Rex. You can see it's a lot more modules because we now support the Neurocom HPC standard, and we have an adapter board so that we can use the COM-Express modules also in the T-Rex. And this really expands the range again, and we can have really big CPUs like Core i9 12th Gen CPUs. That's really a powerful CPU, or a really big Xilinx Zynq UltraScale Plus FPGA. And in addition, we are supporting for GPU SoCs, we are supporting then the NVIDIA Xavier AGX modules, which are used in the smart mirror use case. Here again, I highlighted some modules that were developed in our department, which can also be used in the Rex system. These are totally different modules that are supported by the Microrex. We are supporting, as I said, the SMARC standard, and you have all kinds of different modules that are available in SMARC modules like FPGAs, x86, ARM, domain-specific accelerators, really everything. We can adapt that to the Raspberry Pi Compute Module 4 adapter. We have the Xilinx Kria modules available. We have the Jetson Nanos available. And as I said, you can plug in every domain-specific accelerator like Intel Myriad or Google Coral that maybe all of you know via USB or via M.2 PCIe and have them directly into the system. And then you can compose your appliance really like how you need it. And again, highlighted, which was developed in VEDLIoT now. So a whole bunch of microservers. You need some kind of like metric to decide what is good for me to use. And there we put this overview where each of the different module sizes resembles one line type. And then we have split that up into 5 points where you can decide which one is very, very, very interesting for you. So is size a matter of fact, or do you need a lot of performance? And then you can look at it and say, okay, I want to use the COM-HPC form factor, or I am looking at the COM-HPC form factor, and if I go to this line, I see, okay, I have a lot of performance, I have a lot of architectures. The market share is not that great, not that big at this time, but the size is very, very big, and the I/O flexibility is quite high because I have a lot of space. I can have a lot of I/O. And so you can go about these different form factors and really decide what is necessary for you and what is the right platform for your application. I should have pressed the button when I said the things about choose your point. Okay, going into benchmarks. So, as Pedro already said, we have looked at a lot of different accelerators, and we are trying to figure out which are the interesting ones for our use cases, so for our models. If you go to the vendors, they always say some kind of peak performance value, and you can plot that, and that is what we have done. So these are, for a whole bunch of accelerators, the peak performance values of the vendor. If we put a line through here, this is representing an average efficiency of 1 teraops per watt. We can see that we have in almost every cloud some accelerators that are more efficient and some that are less. But yeah, they are all going around this 1 teraops per watt line. And then we said, very well, we will look into that. And then we started doing our own benchmarks with our own models that are interesting for us and measured the power with our own system. So we didn't use the values that were coming out of the models. We measured them at the supply rail on the REX system. So we used our models, our data sets, and these were the results that we got. And as you can see, the GPU models for the GPU microservers, or really the GPUs, are the best thing that we could use at the moment. We hope that can change a little bit because it's quite boring. Everybody is using GPUs for deep learning and neural networks, so we will see. As you can see, we have some FPGAs in here and some normal processors. This is a little bit different showing. So here we have the different accelerators, and we have the energy efficiency in gigaops per watt. So there you can really see that these NVIDIA platforms really shine when it is about energy efficiency. And you can see for the different nets, the different results. So for different precisions, we get different results. And there also we have an overview what is best to use for us in the project. And we are trying to include new architectures and get them into here, like these GAP8, which is quite new, and trying to figure out if there's something new on the market that we can use. We also did this for a bunch of other nets, but this is only a selection. So, in summary, the VEDLIoT hardware platform provides a very scalable and heterogeneous hardware platform, which is hopefully easy to use, where you can design your system as you like. We have a very big variety of different microservers available because we are relying on industry-proven form factors. We are also enhancing that by developing our own modules in these form factors. We have a tight integration of these microservers with a good communication infrastructure, and this hopefully will lead in the highest energy efficiency and performances. And the integrated management and monitoring capability will enable comprehensive application benchmarking and characterization. By the way, all these benchmarkings were done by hand, so this took a minute or two, and we are hopefully enabling Kenning to work with that, so that we only have to prepare everything and then let the software run for a few hours and get the sensor data back from our servers, and then this will be all automated, hopefully. So that was my part of this presentation. I will now give to Mario. Questions? Yes, thank you. Are there any questions?